Okay, I think that everybody's coming. So let's start. And today we'll talk, in this last talk, we'll talk about concurrency. So we don't talk about Android, we talk about concurrency and about Kotlin. And you could ask me, why are you talking about this? And here's some information about me. So for the last years, I've been working at JetBrains on redesigning the synchronization and communication primitives in coroutines. Did you use coroutines? Yeah, everybody uses coroutines. And what I was working on is improving the channels, the semaphores, the mutexes, so these kind of primitives. And this work, it was partly industrial, partly research work. So I'm also a researcher at JetBrains, so I have some top-tier publications, and I've been teaching concurrent programming for several years. And today we are going to talk not about concurrent code. We are going to talk how to test concurrent code. And first of all, if you ask me, OK, Nikita, I want to develop some new concurrent algorithm. How should I do that? I would say, all right, you need to read a lot of books. For example, these ones. You need to read them carefully. You need to implement many data structures and algorithms. After that, you need to go to the top conferences. You need to read the papers. You need to understand them. You need to build the intuition. But, you know, it's kind of outdated. Nowadays, this year, we have another solution. We don't need to read all these books. We have the guy who knows everything. Maybe. And let's now try to build a concurrent algorithm with the ChatGPT. We need to choose something that is not so trivial, but it's still easy to understand. For example, we can choose a bounded queue. So it's like a normal queue, but of bounded capacity. So you can add items until the capacity exists. And after that, if you try to add a new element, then this add function should return false. And the poll, it works like usual. It just dequeues the first element. All right? And we want to ask ChatGPT to implement this bounded queue correct under concurrent environment. So let's ask it. So here I asked that ChatGPT for you whether he can implement whether he can implement bounded queue based on the standard concurrent linked queue in the Java library. And this is the solution. It suggests a very intuitive way to build such queue. So it uses a standard queue under the hood, a correct concurrent queue, and it also maintains the size counter to understand when the capacity exceeds. So when you add an element, you first check whether the queue is already full. And if it's full, you return false, right? That's what you want. And after that, you insert a new element. And do you increment the size? For me, it looks pretty correct because this queue, this concurrent queue, is correct. It's in the standard library, and the count is also atomic, so nothing can go wrong. And the poll operation, it simply retrieves the first element from the queue, followed by decrementing the size counter. That's the solution we have from ChatGPT. Who thinks that it's correct? No one, really. I think it's correct. Okay, who disagree? We think that it has some mistakes. All right, but how would you check it? How would you check whether this implementation is correct? For that, we need to write a test. And there are many ways to write such tests. And if you take a look at most of the tests, you notice that most of them verify easy-to-follow scenarios, like you enqueue a bunch of elements, you dequeue a bunch of elements, you do all of that concurrently, you check that none of them are missed, or kind of that. And also, you need to run the threads manually, you need to check all these correctness properties manually, and for that you write a lot of boilerplate code. So all the tests, they look the same. And what is the most important, okay, you have a test. You're fine that it covers only simple scenarios. Okay, no problem. You're fine with having a lot of boilerplate code because, okay, it's just a test. You copy, paste the code. You don't write concurrent code every day, so fine. But then this test fails. What can you do after that? The only way to understand the bug, to understand the issue, is to read the code over and over and over until you understand the root cause of the bug. Because usually there is not enough information to understand the error. And it looks like we need some framework that helps us to analyze concurrent algorithms, to analyze the bugs. And how would an ideal test look? Let's say we want to write a test for our bounded queue implemented by ChatGPT. For that, I would say we need to create a new queue and then list all the operations on this queue. So here are the add and poll operations, and we just say, okay, there are add and poll operations. And after that, what I want is to run some magic button, and everything is checked. If we have such a framework, then testing concurrent algorithms would be a piece of cake. And actually, we have such a framework. We have such a framework at JetBrains. We built it for Kotlin coroutines when redesigning all these synchronization and communication primitives. And in Lincheck, the only difference from the ideal test I just showed is that instead of that magic button, we need to say, okay, there is some options to specify the test parameters. We can configure the test, but we usually don't need that. And after that, we just say, check this implementation. And if we check this implementation, if we run this test, then we get an error, something that. Then the framework says, okay, I had this scenario of 2 threads. In the first thread, we add 2. And after that, we add -8. And in the second thread, we add 6. And all these enqueues succeed. And that's incorrect because we had here we had a bounded queue of capacity 2. And here, the 3 enqueues has succeeded. So it's obviously incorrect. And what is more important is that the framework not only provides you a scenario, it also explains you how this error has occurred. So here you see the trace that we start with the add operation in the second thread. We increment the counter. We insert the element into the concurrent queue. After that, we switch to the first thread, we add 2 elements, and only after that, we switch to the second thread back and increment the counter. And because the second thread was interrupted before the counter increment, these 2 additions in the first thread have succeeded. Because they thought that the counter is still 0 and then 1. So they didn't notice that the queue size became greater than the queue capacity. But you know what? Here it was a very simple example because it was trivial. We had bounded queue of capacity 2 and 3 additions, and all of them succeeded, so it was obviously incorrect. But what is correctness in the world of concurrency in general case? And I would like to build some intuition. If we are in the sequential world, then it's simple. For example, this execution, we have bounded queue of capacity 2, we add 1, we add 2, these additions succeed, we add 3, it fails, we poll 1. Is this execution correct? Do you think it's correct? Yes? No? Who thinks yes? Yeah, of course it's correct, because that's how the bounded queue should work. And here we return false because the capacity exceeds. And in poll we extract the first element. So everything is fine. Okay, this one, is it correct? Who thinks that it's correct? No one. Who thinks that it's not correct? So everybody sees that it's incorrect. Yeah, I agree with you, because here the last add, it should return false. All right, but when we talk about concurrent environment, then we have multiple threads. And to understand whether some execution is correct or not, we need another property, and it's called linearizability. The idea is that we have some results, and we want to explain these results with a sequential history of the same operations that doesn't violate the program order and the synchronization between threads. Let's take a look at a couple of examples. For example, here we have a bounded queue of capacity 2 again, and we have 2 threads. On the left, we add A and poll A, and on the right, we add B and poll B. Do you think it's correct? No? Yes? Okay, it's correct, because we can express it with a sequential history. We can say that first, all the operations from the first thread were executed, and after that, all the operations in the second thread were executed. So we can find such a history that explains the results. All right, this execution. The difference is that now in the first thread, poll returns B, and in the second thread, it returns A. Who thinks it's correct? Who thinks it's not? Couple of hands. Okay, it's still correct. We can find such a sequential history. For example, we can say that first add A happened, then the execution switched to the second thread, we add B, we poll A, and we switch back to the first thread and poll B. This is the sequential history that explains these results. And we do not violate the program order. You see, we didn't reorder the operations in the threads, and we do not violate the synchronization between threads, because there is no synchronization between threads here. So This execution was correct. Okay. Couple of more examples. This one. More operations now. Here we add A successfully in the first thread. Then we poll B. And in the second thread, we add B, add C, followed by polling A. Can we find a sequential history that explains these results? So, okay, can you find? Yes? Yes. Yes, many of you have found it. Yes, for example, this one. You can start with the second thread. You add B. Then you switch to the first thread. You add A and poll B. Then you switch back to the second thread. You add C and poll A. And this sequential history again explains the results. Okay, one more. Now the difference is that the last poll returns C. Is it correct now? Who thinks it's correct? Who thinks it's not? Oh, many hands actually. That's because all the previous examples were correct? And you're looking for some incorrectness here? All right. Okay, it's incorrect because for this last addition of C to return true, and for poll to return B, the only sequential history without the last poll is this one. We need to start with the addition of B. Then we need to switch back to the first thread, execute all the operations. Then we need to switch back to the second thread. And after that, if we call poll, it can't return C. So this execution is incorrect because we can't find a sequential history that explains these results. And if your bounded queue behaves this way, it's incorrect. It's not linearizable. It's not atomic. It's not thread safe. It should be fixed. All right. That's what about the correctness? And here, to remind you, it was simple because here was there was a simpler. It's a simple scenario because any order of these operations, it exceeds the capacity. So we can't explain these results with any sequential history because we can't exceed the queue capacity. And here was the trace. I want to show it again. Here was the trace that explains how to reproduce this bug. That's how it works. Who thinks that it's magic? If I were you, I would say, yeah, it's magic, because, come on, I just declared the operations, called some function, and this? Seriously? Of course, it's not a magic, because it works, and we have no concept of magic. Okay. Wow. Actually, I wanted to explain the execution here. I already explained it. Sorry for that. Let's go through it. Let's go through it. And I wanted to show how Lincheck works, how all this magic works. And the framework, it first of all generates a lot of concurrent scenarios. So it's like a fuzzer in this phase. So a lot of scenarios in a random way. So it chooses the operation, inserts it in a random thread, generates a random parameter if it has one, and choosing another operation, inserts it in another random thread, and so on. And this way generates a lot of random scenarios. After that, it examines each of these scenarios in either stress testing or model checking mode. In the stress testing mode, it runs threads and executes this scenario, like you would do with the stress tests. You run threads manually, execute a bunch of operations, and find a bug. But with the stress testing, you can't have a trace that explains the issue. For that, we have the model checking mode. In the model checking mode, Lincheck controls the execution. So it chooses on each memory access, on each read and write, whether we need to switch to another thread or we need to continue the execution. And by controlling the execution, by fully controlling it, we do know how to reproduce it. That's how we get the trace. But OK, before providing the trace, we need to check whether the results are correct or not. And for that, Lincheck automatically verifies whether the results are correct or not. How does it do it? Remember, when we talk about correctness of the queue, or correctness of something else, we didn't say a thing about the data structure. We just operated. We just wanted to find a history of operations. We didn't care about whether it's a queue, a stack, a priority queue, or a hash map. We just wanted to explain the results with some sequential history. And that's what Lincheck does. It tries to find a history, sequential history, that explains these results. And it uses the testing data structure in sequential way to build these sequential histories. Of course, you can specify sequential implementation for Lincheck to ensure that you don't have sequential bugs. That's possible. But by default, Lincheck uses your concurrent implementation in sequential way to understand whether you have bugs or not. And to build that trace, to control the execution, we do need some magic. This magic is called bytecode transformation. Let's take a look at this simple example. We have a counter here, obviously incorrect counter, with the order increment and get operation. We implemented it by incrementing it by 1 and reading the value again and return it. So when you increment it by 1, you first read the counter, you locally increment the value, then you write the counter value. And in the second line of the implementation, we read the value again. And here, in the bytecode, you see, we invoke get field, so we read the field again. That's the bytecode. And to control the execution, Lincheck finds all these get field, put field, and similar instructions when you work with arrays, when you use unsafe, when you use work handles, when you use auto field updaters, when you use something else, all the weird ways to change the memory. And it inserts these functions, like before read, before write. And each time you call the function, Lincheck decides whether it wants to go further or stop for a while and continue the execution in another thread. So for example, if we write a test for the counter and we run it, then we get an error like this one. And here, we start with the increment and get, the second thread. we read 0. After that, we switch to the first thread. We invoke the increment and get. Then we switch back to the second thread. And since we read 0 before, we write 1. It was already incremented, but we write 1 again. And we read 1 after that, and we return 1. And both increment and gets, they both return 1. And this is obviously incorrect, because one of them should return 1, and another one should return 2. And one of the increment, so it's missed. And internally, to find this execution, Lincheck, remember, it inserted this before write method, and each time it decided whether to switch or not. And here, before reading the value in the second thread, it decided to continue. Then, before the write, it decided to switch to the first thread. It executed the first thread without interruption. Then it switched back to the second thread. It called write, it invoked before read again, decided to continue. Okay, actually, it couldn't switch. And finally, we got result 1. That's how it works internally. And in Lincheck, it tries to examine different interleavings, many of them, to find the error. And okay, I told you that we built Lincheck for testing code and coroutines internals. And how do we use it in code and coroutines? Actually, after we started using it, we found a lot of bugs. We have found a lot of bugs in our mutex and our channels, and now all of them are fixed. We actually have new channels, we have new mutex, and we don't have new bugs. Because these bugs were fixed, and a lot of bugs will never happened. And we found errors not only in code and coroutines. For example, we did manage to find a bug in the standard Java library. So there is a double-ended queue. It's called concurrent linked deck. So you can insert and retrieve elements from both ends. And it's incorrect. And the funny story is that the guys who developed it, they tried to fix it multiple times. And finally, they said, OK, we are not going to fix it. We don't know how. And it's fine, because the algorithm behind it is broken. There was a paper published at some top conference. Then the data structure was added to the standard library. And after that, a bug was found in the paper. So don't trust papers. Trust tests. Another example that we found a bug in GC tools, it's another popular library on JVM. And they also had an issue. Now they use Lincheck. So I think everything works fine. And I told you that we used it to build the channels. What I wanted to show is that Lincheck works not only for small algorithms. No. It works for algorithms like this. So it's a state diagram for a part of the algorithms, for a part of the algorithm of the new channels in code and coroutines. And before we implemented the model checking mode in Lincheck, we had a bug in this diagram. And there was a stress test that said, your implementation is incorrect, but we did know it without any test. But how to explain the error, how to understand the bug? And we had to implement the model checking mode in Lincheck to explain the bug. Because even if you can explain this particular bug, spending several days, then you have another one, and another one, and another one. That's why we built the tool. And now we are sure that this kind of algorithm, it also works. And it's in production, so that's cool. So, I want to say you that never use ChatGPT for anything that requires thinking. And even if you use it, please write good tests. If you write concurrent code, use Lincheck. And we are now working on it a lot. We are trying to make it better, to improve the API, the model checker, to provide some support in IntelliJ IDEA. So stay tuned.